So it's in your hands. I'll let you start.
Yeah, so welcome everybody to this virtual tour. So as you will see, let me start first of all sharing my slides so that you can also have a very, very brief introduction. So you should be able now to see my slides. So in case, let me know, I'll keep the chat open in case there are problems so that I can immediately see. Okay, so I'll just start with an introduction to, just very brief introduction to what is the Antimatter Factory, what we do, and then I will leave the floor to Dominique and show you the entrance of the Antimatter Factory. But I don't know if you already had some introduction to CERN in general. You might already seen this picture. This is the map of the CERN accelerator complex. So there are many accelerators at CERN. There is, as you know, the LHC, but there are smaller accelerators that are used to pre-accelerate the proton for the LHC, but also used to provide the proton to the other many experiments that we have, because we don't have only the 4 big experiments that are on the LHC. We have many different kind of experiments. So let me zoom on this part, because we will focus the tour on the AD, the antiproton decelerator. And this is what we also call the Antimatter Factory. And this is the place where we produce antiproton, and we use the antiproton to make the anti-hydrogen. And then we go study the properties of the anti-hydrogen. Okay, I can maybe stop sharing so that, Dominique, you can show the entrance where you are, and then when you start and you enter, I can continue my introduction. Yeah, I can see the...
Can you see me?
Yeah.
Hear me? Well. Okay, great. Yeah. So welcome. I am Dominique Bertola, and I will be your guide today. I started at CERN in the IT department, and then I joined the international relation department. And specifically, I work with the visit service now with the team. So right now, I am in front of this building behind me. You see, it's written Antimatter Factory. It's a strange name, strange because first it says antimatter. So this is something we're going to investigate a little bit today. And Cristiano will tell you more about this antimatter. And factory, strange that at CERN we have a factory. Well, actually we call it factory because this is the place where they make atoms of hydrogen, like Cristiano said before. But it's a very small factory actually, because they make very little anti-hydrogen, because the process is rather long and it costs a lot. So, but they still manage to make these antiprotons and anti-hydrogen. So in a minute, I'm going to enter inside this building, and I will stand in front of one of these little rings that you may have seen on the picture. And this ring is called Helena. So if you have still this reference of the picture, Helena is a very small ring. So, but I stop for now. I leave it to Cristiano. I will mute my camera while I go inside the building in front of this Helena.
Thanks, Dominique. So let me start sharing again the slide. So yeah, I forgot also to introduce myself. I'm a particle physicist, and actually I'm not working in the Antimatter Factory. I'm working in the Atlas experiment. So I'm looking for new particle using the LHC. Okay, I just wanted to start a very brief introduction. I don't know actually what's your background. I just want to tell you, well, as you know, we are living in a world that is made of matter, right? When you look around, you only see matter that is made of a proton, neutron, and electron, right? But we know that the antimatter exists. because we can produce antimatter. We can produce antimatter at the LHC, because when we collide protons, we produce many particles, but we can produce also particle, antiparticle, muons, anti-muons, electron, anti-electron, and so on. So we know that the antimatter exists. But our universe, our world is dominated by matter. And it's still not clear why, because, for example, at the beginning of the universe, you would expect to have an equal amount of matter and antimatter produced, right? But if the antimatter is produced, then where is the antimatter? Why did the antimatter disappear from the universe? This is not completely clear. What we know is that when the antimatter was discovered, when the anti-electron was discovered, they thought it was simply a specular copy of the matter. So electron, anti-electron, they have exactly the same charge, they are exactly the same particle, they just have an opposite charge. Right? Around 60 years ago, they discovered that this is not true, that matter and antimatter behave in a slightly different way. So there is an asymmetry. So the antimatter does not behave in the same way of the matter. And this asymmetry between the matter and the antimatter might explain why our universe, for example, is completely dominated by matter, and why we don't see antimatter in the universe as far as we can see. But given the fact that we are living in a world that is dominated by matter, of course, we don't know what are the properties of the antimatter. We can assume that the antimatter behave in the same way of the matter, but this is just an assumption, and we already prove that this is not true, because matter and antimatter behave in a very different way in some cases, slightly different way. So the experiment that we have at the Antimatter Factory are really experiments that try to study the antimatter. So, for example, what is the gravitational force on the antimatter? We clearly know what is the effect of the gravity on the matter. We can measure since many years, through the attraction between the corps in the solar system, and we know very well how the gravity works on the matter. But what's the effect of the gravity on the antimatter? Is it the same? Is it different? Is it maybe in the other direction? Well, we need an experiment. We need the experiment to study really what is the effect of the gravity on the antimatter, but also, for example, the electronic structure of the antihydrogen that we produce. I don't know if you remember from chemistry, you know that the hydrogen has electron, and this electron can stay at different energetic level, right? And if you provide energy to the nuclei, then the electron jump at higher energetic level. This is what is called also the spectroscopy. And the spectroscopy of the hydrogen is very, very well known. It's also used in astrophysics to study the stars. But what is the spectroscopy of the antihydrogen? Is it the same? Is different? Are the energetic level of the antihydrogen the same of the hydrogen? Well, this is something that from the theoretical point of view, we don't know. And that's why we need an experiment. Well, we need more than one experiment to study all these properties. Let me check. Dominique, are you in front of Elena?
Sorry, just a second. Yes, I'm
okay.
almost...
No, otherwise I can. If you want me, I can continue. Or I was just checking if you want to show.
Yeah, if you want to show, maybe or tell something about the source of the protons.
Yeah.
And
then I have
the target.
a few slides to provide more details.
Yeah.
Yeah. So do you want to start, or should I go?
As you wish. You want to say something about how they make the antiprotons?
Okay.
Otherwise, I'm in front of the Elena machine. So
no, that's fine. So, sorry, I thought you wanted to start to do that.
That's okay. Sorry.
Okay. Then let me start sharing the slide again. Because okay, so we studied the anti-hydrogen. Okay, the anti-hydrogen is made of antiproton and an anti-electron, right? It's relatively easy to produce the anti-electron. What is very complicated is produce the antiprotons. To produce an antiprotons, we need an accelerator first. So this is the CERN accelerator complex I was mentioning before. So there are free accelerators that are used to pre-accelerate the proton. The first one is the LINAC, then the booster, and then the proton synchrotron. In the proton synchrotron, the proton travel already at the speed of light, basically. When the proton reach the maximum speed in the proton synchrotron, they are extracted and sent into a target of iridium. Iridium is a very dense material, non-nuclear. And basically what happened, the proton coming from the proton synchrotron accelerator hit the target made of iridium. They interact with the proton and neutron and electron that are inside. And from the interaction between the proton and from the beam and the proton from the target, you produce a lot of particles. Among them, you produce antiproton. Now, let me just show you what I mean for target. So this is the map I was saying, the LINAC, the proton start going to the booster, then the proton synchrotron, and then finally going to DAD. When they reach DAD, this is the iridium target I was mentioning before. So the proton hit the target. There are some nuclear interaction inside the target, and then you produce particle. And this is a schematic view of what happens. So this is the beam coming from the proton synchrotron. This is the iridium target. You see the proton hitting the nuclear inside, and you produce many particles. You can produce proton, antiproton, electron, pion, and so on. And then what's happened, using magnets, you can select the antiproton, because when a particle enters in a magnetic field, there is a force acting on the particle that bends the trajectory of the particle. The force depends on the mass of the particle, but depends also on the charge. So if you have a positive particle, these are bent in one direction. Negative particles are bent in the opposite direction. Basically, the magnet is used to select the particle that we need. All the particles, like electron, proton, whatever, are sent in one direction, where there is an absorber that absorbs all these particles, while the antiproton are bent by the magnetic field into another direction, where there is a pipe, the proton enter inside, and then enter exactly basically where is Dominique right now, in the AD. So yeah, I can stop maybe sharing.
Okay.
Yeah.
So do you hear me still?
Yeah, very well.
Now, as you see, the environment has changed a little bit. There's a bit of background noise. I hope it's not too difficult for you.
We can hear you very well.
So excellent. Thank you. Thanks, Cristiano. So now I'm on a little platform, and I stand in front of this small ring called ELENA. ELENA stands for extremely low energy antiproton ring. So after the target, the proton will make antiproton. They will create antiprotons. And still these antiprotons, so far that we can recuperate them, we can collect them and bring into this ring, they have still a high level of energy, okay? It's in the order of 3.5 giga electron volts or so. And what the experiments there need, they need very low energy antiproton so that they can trap them with their equipment and with their detector, and then they can do all these measurements. So before the antiprotons arrive to the experiments, they have to cool it down, to slow down the antiprotons. So this is what they do with this little ring, this little machine. Is it okay? Because I have a very small image. Yeah, you see something about the ring, right?
Mm-hmm. Yeah.
Some pieces of the equipment. So the antiprotons turn in this ring, and every turn or so, they will slow down. To do this, first they have to keep the antiprotons in the orbit. Okay, so they circulate in a very high vacuum pipe, and then around the pipe there's different kinds of devices. One of the devices is the bending magnets. So these are the dark blue magnets. I don't know if you see one. And this is called a bending magnet. It turns the trajectory, bends the trajectory of the antiprotons. They also have to focus to squeeze these protons with other types of magnets, which are called quadrupoles. So they have 4 magnetic poles to squeeze the beam. And then to slow down, they have 2 techniques. One is called electron cooling. It is the 2 small light blue towers. If you see it, right?
Well, it's yeah. Okay, now it's better. Yeah.
Yep. And every time the antiprotons circulate below the towers, they bring electrons with one of the tower, and then electrons follow the trajectory along with the antiprotons, and then quickly they recuperate, they collect the electrons. So this is called electron cooling. Another technique is to use a radio frequency system. So there's a cavity here around in this machine where they generate electric field, and this electric field will also cool down the beam. By the way, what we call machine at CERN is accelerator or collider or decelerator. Here we speak about decelerator because they want to decelerate the beam, okay? But in general, we call it a machine. This is what we call machine at CERN. Once they get to very, very low energy, these antiprotons then escape from this little ring and still through a little pipe, and they go in the direction of the experiments. Here in this hall, we have 5, if I'm correct, 5 experiments, and they get these antiprotons, and then it is their turn to collect it and to do whatever they want to measure, okay? We will see one of these experiments called G-bar. At the introduction, Cristiano said that one of the behaviors of this anti-hydrogen is that it may not fall down or feel the gravity, you see, exactly as the matter feels the gravity. So they want to compare, you know, if you drop hydrogen, it feels the gravity, the gravitation. And the big question, or one of the big questions, because there's not only one of the big questions is, does this anti-hydrogen will also fall at the same speed as hydrogen would? And maybe by extension, we could also ask the question, will it fall down, or could be that it falls up? This sounds a very, very strange question, but so far they do not know. Okay, so I think I will let you, Cristiano, to continue with the presentation, unless you want me to maybe show something different on this particular machine. But
no, I think I can maybe say a couple of words also on the cooling, the towers that you show.
Yeah.
So yeah.
Sure.
So let me stop share and start sharing the slide. So the 2 blue towers that Dominique was mentioning are used to, how do we say, cool down the beam. Now, you have to imagine this beam of antiproton as a sort of gas, right? Ideally, what you want to have is, so inside the beam, you have many antiprotons, right? And what you want to have these antiprotons that are moving in this direction with all the same speed. So they have the same energy, exactly the same energy, the same speed. But this is not what happened in reality, because you have to imagine these bunches of antiproton as a sort of gas. So there is an internal movement, basically, right? And what you want to try to do, you want to try to cool down this beam. The analogy is the same of a gas. So imagine that you have a gas in the molecule, right? The higher is the temperature, and the bigger is the internal movement. But when you cool down the gas, the internal movement is lower, right? And then it's lower, 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 lower. So what you want to do with the beam cooling is really basically do something similar. Cool down this beam of antiprotons so that they have basically more or less the same energy and they move in this direction. And this is done with the two towers that Dominic was showing you before. So basically one tower is an electron gun. So it's a system that produces a beam of electron, monoenergetic electrons. So basically with all the same energy. Then what's happened? The beam is accelerated. Here, where there is the curve, there is a magnet, so that the magnetic field bends the trajectory of the electron. Then what's happened? The electrons are directed to the beam, and they mix electron together with the antiproton. Basically, when the two, let's say, gases, electron and antiproton mix, they try to get a sort of equilibrium. And this equilibrium cool down the beam of antiproton, okay? Then the antiproton and the electron reach this area where there is another magnet that bend the electron outside, where there is a collector that collects this electron. Now, the magnetic field is tuned enough to bend the trajectory of the electron without basically affecting the trajectory of the antiproton that are much more massive than the electron. So this is so a beam of electron is inserted. Here, the two beam mix. The electron cool down the beam of antiproton, and then they are extracted. And in this way, you can improve the quality of your beam. And this is very important for the experiment. And this is something similar that happens also in a bigger accelerator like LHC. We don't have an electron cooling at the LHC. We have something that is called stochastic cooling, but it's the same. It's the same kind. It's the same principle. Okay, I can stop sharing. I was just checking the chat box if there are questions. I don't see anything, so I know that you are collecting questions in the Google Docs. So yeah, feel free to post the question that you have in the chat box so that we can promptly online answer the question. Yeah, or something is not clear, we can also provide more details. I guess, Dominic, you are in front of GBAR. I can actually also mention something, because as you can see from the image from GBAR, but also from the Elena before, you see that you have this experiment at ground level, and all these this accelerator and then later experiment that are at ground floor, and they are surrounded by block of concrete, right? The block of concrete is due to the fact that when you accelerate a particle emits radiation, right? This is called the cyclotron radiation. This happens for all the accelerator, also LHC. When a particle have a circular trajectory, basically lose energy. And it's called cyclotron radiation because for the first time was observed in the cyclotron accelerator. And this radiation is emitted on the plane where the particles circulate. So basically, if you stay at the same level of the accelerator, you get radiation. But if you stay above, like for example, where is Dominic now, you don't get this kind of radiation. That's why you have all the block of concrete that surround this accelerator, but there is nothing on top. So in principle, you can also stay there when the accelerator, the decelerator is running. This is a low energy decelerator, low energy experiment. Of course, this does not happen at the LHC. You cannot absolutely enter in the tunnel of the LHC, but this is something that you can do at this low energy accelerator and detector. Yeah. Okay, no, I see very well, and it seems the connection is very nice also on Gbar. That is, yeah.
So far.
Cross.
Yes.
Yeah.
Okay, so you see now, you see I moved from the Elena machine, so decelerator, and I now in front of this G-bar experiment. G stands for gravitation, okay, and bar, anti-gravitation. So this is the setup. So you see these experiments are not as big as the LHC experiments, Atlas and the other experiments, but they are also quite important to better understand why this antimatter has disappeared, for example, from the universe, or there's very, very few somewhere in the space. And also all the other questions that physicists want to try and understand. So this is the setup, and G-bar will get these antiprotons from the Elena machine, and then at G-bar they will make their own anti-electrons, because you remember they want to make anti-hydrogen. So for this they need one antiproton and one anti-electron. So they have to put it together. So G-bar experiment has also, let me see if I can turn my camera. Yeah, you see below these big concrete blocks there's a little barrack, and down concrete blocks. This is the place where they will make the experiment is not running now. They will make anti-electrons, and these anti-electrons will then be accelerated with a LINAC. LINAC means a linear accelerator. So with this linear accelerator, they will accelerate the anti-electrons, and then anti-electrons will meet together with these antiprotons, and this will make anti-hydrogen. Once they've managed to make this anti-hydrogen, they will trap it into a kind of box. They call it trapping. So that then, and this will be at very, very low energy. If I remember well, I think that G-bar wants to have anti-hydrogen at 1 kilo electron volt or so, which is very, very low energy. And this anti-hydrogen will be trapped in the box. It's not huge box, you know, and then they will drop it, and they will measure the time it takes to drop. They will drop it by something like 20 centimeters or so. It's not from the Eiffel Tower, just 20 centimeters. And then there's also all sorts of detectors, because they want to be as precise as possible to measure when they drop the anti-hydrogen and when the anti-hydrogen will reach the bottom of the cage. So there's also around this box, around this trap, there's also detectors to measure these things. And they have to repeat it over and over, because they cannot measure at first, you know, they have to collect the data and then to analyze all this data. So this is another process which sometimes take long, and they repeat that. In this building, there's a competitor. There's another experiment on the other side. They also want to prove the gravity with anti-hydrogen. So good to have this competition. Let's see. When I say competition, it's like you know, the big LHC experiments. They compete, but they also work together, and they also sometimes confirm if one of the experiments sees something strange or not. They will double check with the other experiments. So this is good, and this is science in general. This is how science works. Okay, I don't know if you have questions, not maybe directly to me, but I remind you can use the chat probably. and you can ask questions that Cristiano will probably read.
Yeah, I don't see anything in the chat.
There's no questions so far.
No questions so far. Yeah.
Okay. Are you still there? I believe so.
I believe so. I see they are connected. So
yeah, sure. No, this was my little joke. Okay, I don't see what else I could. So around this setup, I'm not sure if the quality of the image is good enough, but you must see lots of spaghettis, you know, cables, wires, and this is typical environment in a could be antimatter experiment or LHC or whatever experiment it is. They have lots of cables around, and could be high voltage, could be signals, could be also power cable to power the magnets and to power the equipment which is there. And sometimes people ask, oh wow, there's so many, and how do you recognize this cable? Are you sure that they are all used and useful? And my answer is yes. I hope that they understand and that they also need all these cables. But believe me, yes, they do need all these cables. There's lots of signals from the detector, from many different sensors which are around this setup. And yeah. So once they collect the data, this is first analog signals, then they will digitize the signals. And once the data is digitized, is sent through all these electronics and this computer environment locally here. It is sent to the data center, which is, let's say, how much? 200 meters from here? Not very far. And then the data is stored in the data library, in the magnetic tapes and hard disks, and then they can study, they can analyze this data, and also they can share the data across the network. And not all the antimatter experts are here at CERN or at GBAR. So they may stay in their own institute, research center, and they can also contribute and analyze the data. And by the way, this is also true for the other experiments, like the big experiments. When I say big, is the big LHC experiments, ATLAS, CMS, LHCb, and ALICE. So this works almost the same, not the same size, but very, very interesting, believe me. There's a bit of noise around, at least myself, I can listen this noise, because they are more or less setting up or testing their equipment to prepare when they will have beam of protons and antiprotons. And this should be sometimes next year. I don't know if Cristiano knows more about this this timing or this scheduling, but
no, not for the AD, no, but yeah, that should be around.
But for the LHC, yeah. This will be also next year.
Mm-hmm. Yeah.
Okay. So that's it for me. Do you want to add something or correct?
Well, no. No, I think it's fine. I mean, I don't have anything to correct, or well, I can maybe add something about the AD, the accelerator. I mean, yeah. Just let me just share the slide, because actually, where Dominique is now is exactly on top of the AD, because Dominique entered here. This is the Elena ring. Then he walked here where there is GBAR. And basically, the path is made of block of concrete. You remember the block of concrete that I said before? The Elena is surrounded by block of concrete, but nothing on top, while the AD is surrounded by vertical block of concrete, but also horizontal. So basically, the path, the walkway around the AD building is basically on top of the AD accelerator. So Dominique is exactly here, exactly on top of the AD. Now we cannot enter in the AD at the moment for safety reason, because I think there is also some test beam, so there is a radiation that is not open. But this is basically what you will see. So if you enter in this sort of tunnel made of a block of concrete, simply is not excavated like LHC, you see this is the AD. And these are basically the same kind of magnet that you also saw already in Elena. So the blue magnets are the dipole magnet that Dominique was mentioning before to bend the trajectory of the beam, because this is a circular decelerator. So you need these magnets that are used to bend the trajectory. You see here also the detail about the magnet. What you see here, there is a pipe, and this is the beam pipe where there is a vacuum inside, and the antiproton circulate inside this vacuum pipe. And what you see in red are the quadrupole magnet. Now you can really see very well here, but you see that the blue have one pole and another piece of magnet that is the other pole, while the red magnet have 4 poles that you cannot really see very well now, but these are the quadrupole magnet. You can maybe see here. Okay, you see this is red, and you see one pole, another pole, and you have to imagine the same on the other direction. So one, so 4 poles. And then you have, as you see here, you have many things. You have not only magnet, but you have many also systems that are used to monitor the beam, to check the position of the beam. So these accelerators are not very simple machine. They have many systems that are controlled by in the control room that are really used to understand in every second what is the position and the quality of the beam, and all the property of the beam are analyzed, so that you can always tune and try to improve as much as you can the property of the beam. Yeah, just wanted to show you this. I see you are now in front of actually the entrance of the AD, but as you can see, there is we can see very well the red light that say there is radiation. So yeah.
Yes, I moved while you were giving this other extra information. I moved in front of the access control of the AD, of the antiproton decelerator. If you see me, I'm in front of this little box here. So if I were to enter, and if I add the authorization, now it's blinking. It says closed. As you said, they have test beam, which circulates in the machine. But under controlled access, or I could let me check. I could swipe my badge in front of reader. This little SAS would open. First door opens. I enter in the SAS. I stand in the middle, not move. And then inside, there's the iris scan. So it's a biometric control. It will scan my 2 eyes. And provided that I have all the training, the authorizations previously signed, the other door will open on the other side, and then I can enter inside the AD and to work or to do some operation on the machine. Okay, and sometimes when there's no beam at all, nothing special, let's say long shutdown. Long shutdown could be, 1 week or a few weeks, to do some maintenance or to do some change in with some pieces of the equipment inside the AD, inside this ring. They may open completely the doors. In this case, this is really free access. So I do not say